Draw a figure to show the splitting of d orbitals in an octahedral crystal field. Now, this is very interesting in many respects. Why? First of all, you have to appreciate that splitting of d orbital does not mean that you are trying to cut d orbitals and there are 5 and now after cutting they would become 10. No. All it means is that, see, d orbitals are degenerate. What does that mean? There is a word called degenerate, and degeneracy means that they all have same energy. So, if you see 1, 2, 3, 4, 5, you have dxy, dyz, dxz, dx square minus y square and dz square. Now, which of these d orbitals has the maximum energy? Actually, each of them has same energy. That is why we use the word degenerate. So, if you have an isolated atom or ion, transition metal atom or ion, all the 5d orbitals have exactly the same energy, which are in the same shell, right? Now, in the process of forming an octahedral complex, you find ligands are approaching along x-axis, y-axis and z-axis. That's how you get octahedral geometry. As ligands approach, now because of their interaction, because of electrostatic forces, these d orbitals are no longer degenerate. Now you find that they start exhibiting different energies. And what happens? See, what happens is each of these d orbitals is affected to a different extent. Like, say, for example, you find that two of them are more strongly affected. Which ones? Dx square minus z square, y square and dz square, and dxy, dyz and dxz. They are not equally affected, although all of them are. So you find that they now split. Splitting in the sense doesn't mean that they become from 5 they become 10. As I said, what happens is that they are now at two different energy levels. So while an isolated atom had all 5d orbitals at same energy level, now within a complex you find that these d orbitals are in two different groups. Now we call them EG and T2G. Oh, that's easy? Yeah, it's easy. And this is the so-called splitting of d orbitals in octahedral crystal field. Is there a difference in energy? Yes. This difference is called by a very special name. People love to call it delta O, or this is octahedral crystal field splitting parameter. Okay, very interesting. And can I say that there could be, there could be a line which you could call as an average line. And this line actually goes by a very fancy name. It is called barycenter. Barycenter. What is barycenter? It means it's a weighted average of energy, kind of. You can say if you take a final average of all these energies, this is barycenter. That would be the average increase in energy of all the 5 orbitals. Fine. As compared to barycenter, you find that T2G orbitals are a little less. This distance is 0.4 delta O. Oh wow. And you find EG orbitals are slightly above by how much? 0.6 delta O. So as compared to barycenter or the average energy, the stable ones are 0.4 delta O below and the relatively less stable ones are 0.6 delta O above the average energy level or the so-called barycenter. This, dears, is the very exhaustive and very beautiful splitting of d orbitals in an octahedral crystal field system. I also have some write-up on that. If you wish, you could take screenshots. You might find it useful. This one. And then this is the story, pre-written story for those of you who are interested. And a so-called official diagram. I find it very dirty. I hope I have drawn a better diagram myself. Right? But nonetheless, it's all there for you.